welcome to Cactus Muffs. Today I just want to have a quick chat about cylindrical elements and working out the general balance for cylindrical coordinate systems and then applying that with mass balance in order to get a continuity equation. So let's begin. So I share my screen and go to this one. Okay. So here we have a coordinate system XYZ with a cylinder in place, and we see that there is a differential volume element here in the cylinder. And we can do a general balance around this differential volume element of the cylinder in order to generate a general balance. So looking at this system here, we can firstly identify a couple of things here. So if you look at this top surface here, this one here, that is a Z surface because the normal to the surface is Z, and obviously Z is constant on the surface. This surface here, if you look at it, any points on this surface are at a constant value of theta. Remember, theta is measured from the x, you have the xz plane. So all these values, theta is constant here. And then if you look at this plane here, all the values, all the points on this surface are a constant value of r away from the origin, from the center, right? They're all constant values away. Because it's on the, if you can imagine, it's on the curved surface of the cylinder. So we essentially have a z surface on top, a theta surface at one of the sides, and a r surface at the front. So therefore, back. We could redraw the system again. It's like this. It's going to be a terrible drawing. I can already tell. And as we've said above here, this is a z surface. This would be our theta surface, and it's our surface. We also have, because of the differential volume element, we also have differential volume terms involved in here. So I see here we have, this is, if you imagine, the origin is somewhere along here. Sorry. Right. It is in green, differentiate, actually a purple. If you imagine this would be kind of the radius from the origin, right? So this would be dr term here. This is obviously, if this was 0.0, this is obviously going to be an elevation, so dc here. And if you think about it, this time I'll change color. If you think of the angle involved here, right? This is actually a differential angle d theta, right? And we know that the distance from the origin to a specific point is given by r for cylindrical coordinate systems. So in fact, this curved length is actually just given by r d theta, right, from geometry. So now we've labeled all the dimensions of our differential element. We can now go ahead and work out the areas of each surface. So for the z surface, we have an area of AZ, which is given by, as you can see here, this will be r d theta multiplied by dr. So I'm just going to write that as r d theta dr. For the r surface, just the one here, we have r d theta multiplied by the elevation dz. So we have r d theta z. And for the theta surface at the side here, see the same thing applies, same analysis, and a theta area, and this is drdz. dz. Well, it's hard to write. And for the volume of this differential element, delta v, that is given by equals. It's just, if you imagine it, this is like the area of this like curved region multiplied by the thickness. So that would be r d theta. R d theta. Oh, r d theta dz multiplied by the thickness. So that would be dr. Yeah. Seems I'm getting better drawing up d's and thetas now. Alright, now we move on. Okay, so now that we got this, I'm just gonna clear this to get a bit more space. We can now construct our general balance equation. So we have the partial with respect to t of concentration of B multiplied by the volume. Because all the terms in the balance have to be in terms of an amount of the property B times the rate of the property B. Also, one thing I want to mention, concentration of a property. It's a little bit of a weird concept to get your head around, but the way I like to think about it is this: a concentration is given by, as you see in the notes, as m over v, right? A concentration of a property is pretty much telling you kind of how dense or how much of a property there is in a region, right? And the way that I think is the best way to think about it is think of this density of this property B as a density function, right? And say if you have a region here where, you know, it's fire, right? This is some really good fire. And you have another region here where it's ice. This is me trying to draw a snowflake and failing. We can describe these two regions as by saying that the density of a property, in this case, right, let's take the property of B to be temperature, right? That makes more sense. We can describe this place to be of a high temperature, right? That's what we usually say. We usually say that the temp is very high here, and the temp is very low here. But we can also say that the density of the property of temperature is very high here because, you know, there's a high amount of temperature here, so it's more dense. There's a higher density of temperature in this hot region compared to this cold region, right? So that is all this concentration means. And obviously when it comes to when our property is mass, this is nothing more than the mass density. But when you get to like say if this B property was temperature, this will be a kind of density function of temperature. So it's a little bit of a weird kind of thing, but it makes the actual derivations of the general balance a whole lot more easier than if you were to do it a different way. So it's quite an important thing. You can get your head wrapped around that. So this is equal to, now we need to analyze the fluxes at each of these points. So if you imagine, we need to do in this case, we need to do a 3D flux, 3D balance, 3-dimensional balances, because we got variations in all 3 directions. We obviously have a flux coming here, which has a magnitude of JBR. We have a flux coming in this direction of a magnitude of JB theta. And we have a flux coming from the top with a magnitude of JBZ. So we can use this information to now construct the full kind of general balance now. So obviously all the terms have to be an amount of a property over a unit time. So if we first consider in the z direction, so we're up in the elevation, we have the area in the z direction, which is given by, as you saw before, dr d theta r, and then multiply that by the flux, which is given by j bz, and then this needs to be, so this is the input going in, so this will be input, this will be evaluated at z minus the same thing, so dr d theta, terrible handwriting for me, sorry guys. Flux across in the z direction. This time, obviously, because there's an output, we're going from here, where it's z, to here, where it's z plus a small change in z. So this will be evaluated at z plus delta z. Yeah. Okay, and then repeat the same thing for the theta and the r directions. So we get the r direction. Obviously, when you write this down on your paper, it's going to write it down a lot quicker than I don't know. Maybe I should invest in a touchpad. I don't have that kind of financial backing. Yeah, I am only but a broke student. And then same again here. If this is r, this needs to be now evaluated at a distance of r plus delta r. Plus delta r. finally for the theta direction, so the area in the theta, we've got d, there's a d there. D theta. I'm going to show you that is a b as well. It's just I can't write. dr. And finally, same thing applies here. Oh, this isn't the wrong direction actually. Yeah, this should be theta here. This should be from R to wait, no, wait. No, this is the radial direction, obviously. I'm being silly. Yeah, so this is R and R. This would be theta and theta plus theta. Sorry about that. I got confused on my own train of thought, which isn't very good. I'll redo these things as well. So, so this is from Z to Z plus Z. This is from R to plus plus a small change in R. And obviously this is from theta to theta plus a small change in theta. Now, first move to do here, the next move for the next line that you would want to write here would be you'd want to divide through both sides by the volume here. You can take the volume out here because of obviously volume, all the terms in the volume as you saw before, independent of time. Oh, that reminds me, we forgot the generation term. Don't forget the generation term. There you go. And when you do divide by the volume, obviously I'll write down the volume here again for you. R d theta dr. So of course, when you do that, then you do divide by volume through both sides. One thing you have to make sure is you can't cancel out the R here with these R's here and here, because both of these R's are being evaluated at different things. So the R here is being evaluated at R, which, okay, but then the R here is being evaluated at R plus delta R. So this R is actually R plus some delta R. So when you come to cancel, just be aware of that. Be aware of what you're evaluating at and how sometimes you just can't cancel with the things. So if we were to cancel now, we would have, obviously this term would go cancelling with all with respect to all the z's. Yeah, dr would go, d theta would go, and R would obviously go here as well because it depends on R. But now this whole thing, there'll be a remaining of a dz term. So this is going to be super messy. So bear with me. I will write it out in full. When you do it here, it's best to leave the 1 over r outside, but you can cancel out the d thetas and the gz's because they're not they're independent of r. So you'd have here I'd probably just take like a bracket out and be like 1 over r for here. And then finally for the theta terms, yeah, both of them can just go. And oh, I didn't cancel this out as well. Silly me. Yeah, same here as well. But just to make things a lot more manageable, I would still put this outside as such. And obviously, when you divide through by volume for the generation term, the volume just goes. So, right, a lot of cancelling and messing about like this. Okay. So after doing all those cancellations, you will eventually find that everything just reduces down into, oh, before that as well, when you cancel, it's also a good idea to put everything into the form of the definition of a differential, which, if you remember from watching the videos, if you have something like df dz, dx, sorry, I said dz, and that's the same as evaluating f at x plus delta x minus f of x divided by delta x. So you got this definition. If you can, once you cancel, then you take a minus out and kind of rearrange everything. You will eventually form something like this. You'll eventually see that partial is at the time of CB, concentration of a property B, is nothing more minus JB GB. I'm just going to walk you through before applying the definition. So this is like the one step before applying the definition. So you've just cancelled out all your d theta, drs and whatnots, and you just put it into the term for the definition of the differential. Fit it in. Yeah. And then finally, got the theta terms coming in. This is an apostrophe, by the way. I just realized this bit is really terrible. I'll redo that bit. Actually, just finish this bit off. The generation term here. Just redo this bit. The story. J B. Then if we take limits and apply the definition of the differential, as I showed before, all of this reduces to become nothing more than partial of the concentration with respect to time is equal to, becomes nothing more than d3 partial of JB z direction over z, d partial of z minus 1 over the r of the partial of j, the flux in the r direction, so the direction of the radius, multiplied by r divided by dr. Obviously, because for this term we had, it was like r jbr evaluated at r plus delta r minus r jbr evaluated at r. So you take the function to be r jbr. So when you apply the differential, you get into that term. So it's very similar to also what he did for, I think I believe it was a shell balance in the lecture notes. So if you look back to it, you'll see he's done the same kind of thing. And it's the same sort of analysis that you do here as well. Minus 1 over r partial of the flux in the theta direction. Okay, and then obviously your generation term here as well. So this is the general balance for cylindrical, a cylindrical differential element, using, of course, cylindrical coordinates as we've done here. So you can clap yourself on the back for doing this, but this is not the end, unfortunately. This is not the end, as we still want to do the continuity equation, so we want to do the mass balance. So to do that, we pretty much just have to change this property. So this property, sorry, not property, yeah, property, yeah. Property of B, if we make that property into a mass, so converting this general balance into a mass balance, we see that obviously mass can't be created nor destroyed. So the generation term becomes nothing more than 0, because conservation of mass. If you imagine, as we said before, concentration of B. Now that B is a property property of mass. Mass is this, and this is, as we said before, is the density, and this density function, as we said before, was the density function of property B, but now the property B is mass. This is nothing more than the mass density, right? So this is just normal density that you all know, and we also know that the flux of property B, the diffusive component of it, diff, well, terrible D, there's no euphemism as well, diff because nothing more than 0. Therefore, flux is given only by the convective component, so of B, which is nothing more than the concentration B multiplied by velocity vector. And as we said before, concentration is now density, so this is nothing more than density times the velocity vector. So now that we got all of these, we got all our components in, we can now say that this velocity vector, in the Cartesian coordinates, the components would be, as we saw before in week 1, it would be something like Vx, Vy, Vc, but in the cylindrical coordinate system, which we used heavily here, and we have used, the components would be, it would be dr, d theta, and sorry, not dr, vr, v theta, and vz. So if you this is a z by the way, not a 2, just realized. Not terrible handwriting today, isn't it? So let's go all this. Okay, so so putting in all the elements, we find that this is nothing more than partial of the concentration. No. Yeah, partial of the concentration with respect to time, which now concentration is density, so that's what it is there. And that's equal to, remember we had the term of minus djb z dz. So, and we said that the should probably not have erased actually. We said that the flux is this. So applying the z component of the flux, we have velocity in the z direction, right? Minus 1 dr d dr density velocity in the r direction minus 1 over r. No, what's up at the end, Josh? No. looking at my notes that are written as well, so it's kind of hard to write and do both. So yeah, so this is, oh, one thing I forgot here as well, there is an R, see, because this was R multiplied by JBR. And obviously JBR, the R component of the flux vector is rho VR, but you still got the R there, so don't forget that. So yeah, this is it. Maybe I should write this out as well, just to help. So in cylindrical coordinates, this is the components are made up of you know, theta, you know, v side. Yeah, so eventually that's what it is, that's what it comes down to. Yeah, so this is in fact the continuity equation for a cylindrical element. Well done, you have derived it. Woohoo! Clap yourself on the back. But yeah, hopefully that was helpful. Until next time.